Please welcome to the stage Applied Science Director, AWS Identity, Neha Rungta.
Hi, everyone. Welcome. It's great to see you here at Inforce. My name is Neha Rungta, and today we are going to have an action-packed session on how AWS is using techniques that date back thousands of years to help prove, yes, mathematically prove the access controls of the security for your data and workloads. For the past several years, AWS has been applying automated reasoning for the security in the cloud and security of the cloud. We call this provable security. There are several capabilities powered by automated reasoning: IAM Access Analyzer, S3 Block Public Access, and VPC Reachability Analyzer, to name just a few. Earlier this year, we launched the proven correct version of the IAM authorization engine. And then I'm going to talk about how we are using that same innovation to provide security to the authorization of your resources and your applications through the use of the Cedar policy language. So a little bit about me. I've been at AWS for about 8 years now. Before that, I used to work at NASA Ames Research Center. My job was to apply automated reasoning techniques to aerospace applications. One example of a project that I worked on was to prove correctness of the algorithms used in collision avoidance systems on commercial aircraft. It was critical to get the correctness of those systems right. And since I've been at AWS, I've been applying those same techniques to prove the correctness of cloud. And I'm very excited today to share this amazing journey with you. Now, before we talk about automated reasoning, let's talk about manual reasoning, the kind that we did in high school, the kind that we did to learn about the Pythagorean theorem. So a recent discovery of a 3,600-year-old tablet revealed that the ancient Babylonians understood the Pythagorean theorem. A quick refresher: the Pythagorean theorem states that the square of the side opposite the right angle is equal to the sum of the square of the other two sides. Now, it's interesting because this tablet dates back 1,000 years before the Greek philosopher Pythagoras was even born, and he is widely associated with this theorem. Now, the tablet does not express the theorem in its algebraic form as we know it today. But coming up with the triples that were on the clay tablet required an understanding of the general principles of the relationship between the sides and the hypotenuse. Now, it's interesting because what were they doing with it? Researchers actually believed that the ancient Babylonian land surveyors used the theorem to draw accurate line boundaries, while the Greek used it to map out the night sky. It's been in use thousands of years. People assumed for it to be correct. Until Euclid, a mathematician in 300 BC, proved it correct. How did Euclid do it? Did he fuzz all the triangles? Did he do an audit of all possible right-angled triangles? Or did he come up with an AppSec review for the process? Hey, does my triangle meet my threat model? Or did he analyze all the logs using fancy data analytics to say, oh, do my triangles conform to my theorem? No, he did none of that. He used symbols and geometry to represent many concrete values and prove the correctness of the theorem. The theorem holds for all possible right-angled triangles, infinite triangles, and he did not have to observe all the possible triangles. Today, we actually take this theorem for granted. There are many geometry proofs that build on this theorem. We build even more complex proofs on this theorem. Fast forward to the modern day, we are still doing proofs about geometry. But rather than do it manually, we are using automated proof techniques to do it. OK, I know what some of you are thinking. Softwares aren't built out of triangles. Why are we talking about triangles? You're absolutely right. Software isn't built out of triangles, but the same techniques we can use to prove correctness of software itself. The inputs to the correctness of software are an implementation and a specification rather than a triangle. Here are the characters in play when you have a software system. We have a human, generally a developer, who implements a piece of software. Oftentimes, there is another human, an architect, who writes the specification of what the system should do, what it is intended to do. And the goal during the whole software development process is to get the implementation to do what we want it to do. The architect writes the specification in a natural language, possibly English or something else. They write it in a document, maybe with a crayon on a napkin, maybe it's in their head. There's lots of possibilities. Then the developer codes up that implementation. And the processes that we use today to connect the implementation with the specification involves things such as code reviews, design discussions, testing. But to go a step further, to be the modern day Euclid, you can prove what the software does. No, it's not magic, it's math. The implementation and the specification are translated to mathematical logic. In most modern systems, this translation process is automated. The moral equivalent of that is that of a compiler. You can think of how the software is translated to mathematical logic. Now, once the translation process is done, you can take both the implementation and the specification and give it to an automated reasoning engine. And the reasoning engine will tell you, yes, the implementation satisfies the specification, or no, it doesn't. So that is the field of automated reasoning. It automates what Euclid and others did manually. It uses algorithms to construct and audit proofs. It automates the manual reasoning. But in the same way that Euclid's proof covered infinite triangles, all possible triangles, the algorithms of automated reasoning allow you to cover all possible inputs, all possible scenarios for your software. Now, proving something correct requires investment. The first step to translate a given domain, a Java program, a design diagram, IAM policy, network configuration, any domain, to mathematical logic is to figure out what are the right tools and techniques to make this magic happen. How do we represent both the implementation and specification in this language? To come up with the right representation requires expertise in automated reasoning, and it also requires an understanding of the domain that you're trying to translate. Think about it. You have to understand two key pillars. Then, as the implementations get larger, once you've done all that hard work of translations, your implementations will get larger. the specifications will get more complex. And that's where the automated reasoning engines will run into scalability challenges. It requires a combination of science and engineering to extend the algorithms, to develop new algorithms, or sometimes to adapt the algorithms to your domain, to new domains. Now, let's look at some examples where we do apply automated reasoning. Hardware verification of bit slice ALU design. In 1994, the FDiv bug, the floating point division bug in the Intel processor, based on reports that were published by Intel, led to a $500 million impact. And at that time, Intel knew that there was an increase in the number of bugs that they had in every generation of their processor. Their report said they knew there was a 4-fold increase in the number of bugs. And they estimated about 8,000 bugs in the Intel 4 processor. They knew it, but they knew that the pre-silicon simulations were not sufficient to catch all of these bugs. Testing was not sufficient because the state space was so big. For testing an adder, it required 2 to the 160 possible pairs of floating point numbers to test fully that adder. That's when Intel and a lot of the other hardware companies started investing in automated reasoning, because now they could prove the correctness of the chip, the design of the chip with respect to the specification. Another example is aerospace and medical devices. They have traditionally invested in automated reasoning because correctness is critical to human life. And now, in the cloud, as we run more and more critical infrastructure, workloads, applications, we have both the responsibility and the opportunity to apply these same techniques to the cloud. We apply automated reasoning to prove security of the cloud and security in the cloud. We call this provable security. And we automate proving security properties expressed in mathematical logic. We construct the proofs automatically, and we audit the proofs automatically. Let's look at an example of how we are using automated reasoning to help you protect your data. Amazon S3 Block Public Access. It is a security guardrail to help you protect your data in the cloud. You can turn on S3 Block Public Access either at the account level or at the individual bucket level. And now, every new bucket you create, BPA is going to be turned on by default. This is powered by automated reasoning. What we want to prove here, mathematically prove, is that my S3 bucket policy does not grant public access. Not today, not in the future. The way we express this security property in mathematical logic is that all requests allowed by your policy never grant public access. So this security property is what we say is expressed in mathematical logic. Let's break this down a little. To say my S3 bucket policy in math, we have a function allows that takes in 2 inputs, a policy and a request. And the function returns true if the policy grants access to that request. To say never grants public access, we have a function public that takes in as input a request, and the function is true whenever the request is public. So we negate it with the not operator. Finally, the upside down A. That means for all values of R, all possible requests, infinitely many requests. we construct a proof that the implementation of your access control, a S3 bucket policy, matches the specification that it is not public. In fact, we have an algorithm that says that this proof will get constructed and audited in milliseconds. Let's suppose we are able to represent every possible request on this slide. Let's just imagine this. Let our imagination run loose. All possible requests, infinite requests. Some of those will grant access and others won't. Our goal is to build a proof that accounts for all possible requests. The start of the proof is that any request that is granted access may not be public, while any requests that are public are denied access. You know, so good so far? But to build such a proof, we need to define public. What is public? And it's not as obvious as it seems. Suppose you give your neighbor a key to your house. That's not public because you know them. You trust them. But if your neighbor could get into my house, I would consider that public access. I don't know your neighbor. I don't trust them. And as we wrestled with this notion of public, we realized that we keep coming back to the notion of trusted. So we leaned into it. We replaced the notion of public and not public with not trusted and trusted. What makes trusted special is you can specialize it. We can do it by examining the policy of who do you trust. If your policy explicitly allows access from organization 123, then we treat it as not public because it's trusted. But if you grant access to username Alice, that is not trusted because anybody could create a user named Alice in their account. Trust requires specificity. You can trust Alice from organization 123. You can trust Alice from account 456. But you cannot trust a generic user named Alice. Now, once we've proven your policy only allows trusted access, how do we get back to public? We need an additional intermediate result. We prove that all trusted requests are not public. And now we can fit these two results using logic. If A implies B, B implies C, then A implies C. Therefore, all the allowed requests are not public. So the intuition of automated reasoning techniques is how you can prove your S3 bucket policy does not grant public access. With one click, we construct a proof on your behalf, and you get a powerful security guardrail. There are several managed services that use automated reasoning and provide you these capabilities. S3 block public access is the one we looked at. There is IAM Access Analyzer, VPC Reachability Analyzer that allows you to prove properties about your VPC networks. They do the same reasoning for you to prove the security properties of your networks. Next, we are going to see how provable security is built into something you use every day with every API call you make to AWS. IAM. It's a fine-grained permissions management system which lets you define who has access to what. Earlier this year, we deployed a proven correct version of the IAM authorization engine. And you did not notice. Nobody noticed. OK, so if nobody noticed, why are we talking about it? The equivalent of this is if we replaced the engine of an A380 while it was flying and nobody noticed. That's what we did. Because IAM processes every request to AWS. IAM processes 1 billion requests a second. We have millions of customers, thousands of resource types, hundreds of AWS services. IAM just works across different regions, availability zones, all the way to the edge. At this scale, we want to raise the bar on security. So we apply automated reasoning to prove the security and correctness of the IAM authorization engine. We construct and audit proofs of the core security properties, such as deny trumps allow, among many others. We are doing here what Euclid did for the Pythagorean theorem. We are proving the correctness of a battle-hardened, time-tested system. We knew it to be correct, but now we prove it to be correct. It's reasonable to ask, why are we doing it? Raising the security bar is an example I've talked about. Another one is we believe that the ability to codify design principles as theorems is powerful. And we've been doing this across the AWS infrastructure. S2N is a lightweight TLS implementation that AWS did, encryption SDK, boot code that's running in our data centers, free RTOS, which is an operating system that runs on IoT devices, proving its memory safety, and now the IAM authorization engine. We take the design principles that are in the heads of developers and architects that have written down on the piece of papers that are institutional knowledge, and we codify these. Once we codify these, we can actually prove the correctness of these design principles. These design principles now turn into theorems. This is powerful. Once we can do it, it opens a whole bunch of opportunities. With proofs, we can do aggressive optimizations. At the scale of 1 billion calls per second, which is trillions of calls per day, every nanosecond matters. Every nanosecond. The more we can shave off, we can provide a better customer experience, we save on our compute resources, and we can do these optimizations with a high degree of confidence. For such a critical component that's running at scale, it's important to ensure backwards compatibility. We can now exercise extreme caution with confidence, quickly. These proofs, they run in a developer's IDE continuously. These proofs run in the CI/CD pipelines. They're part of the development process. They're part of codifying the design principles into the development process, in the same way we do with bits and pieces that are manually done. Let's get into the nuts and bolts of how we did it. There are 4 basic steps. The first one is to say, how do we write the formal specification of what IAM authorization should do? This may sound a bit backward, because it's a system that's been living and breathing for the past 15 years. It scales. It serves a variety of use cases. It's time-tested. The purpose of the specification is to take the elements of the design that are knowledge and take the history and formalize the knowledge in precise mathematical logic. Normally, the specification is written up front, because it's the intent of the system we are building. But now we formalize the specification of what the system already does. We use a rich set of resources, public documentations, code, comments in code, the behaviors that we observe for the different policy evaluation types. We take all of that information to create that specification. Here is a taste of what a specification looks like in IAM. This formal specification is for wildcard matching. Wildcard matching walks over a string to see if it matches a pattern. When you come to a wildcard, a star in the pattern, what makes it hard to see if it matches is you don't know how many characters a star will match to. A good implementation really tries to make this process efficient, because you don't know if the star will match to 0 characters, 1 character, 2 character, 10 character, 100 characters, 1,000 characteristics. A whole bunch of heuristics often go into wildcard matching algorithms to detect the number of characters efficiently that it will match to. But in the specification, efficiency doesn't matter. It doesn't matter at all. That helps us make it small, concise. It's precise and concise. These 2 lines represent wildcard matching in all possible ways. It considers, does it match 0 characters? Does it match 1 character? No. Does it match 2 characters? No, let's keep moving on. 3 characters? No, let's keep moving on. And it blindly marches on until you eat the whole text. Now that we have a formal specification, we can prove theorems about the authorization. Here are 2 core properties of the IAM authorization engine: deny by default and deny trumps allow. Why are these key to the security of access control? Deny by default ensures the security of your workloads and data. Because whenever access is allowed, there is an explicit reason for it. To allow or grant access, someone has to go in and write a policy that explicitly grants access. Deny trumps allow is very powerful, because when you see a deny statement, deny Bob access, you know that access will be denied. There will be no allow statement that comes before or no allow statement that comes after that will trump this deny statement. It's not dependent on ordering. With the specification, we can prove these properties even before we implement them. Deny by default is a design principle. I talked about the equivalence of design principles and theorems because there is not a single place in your specification where you can say, oh, this is deny by default, or this is deny trumps allow. A theorem is a design principle that holds globally. When you prove a theorem, you're actually proving a design principle. And it is tempting to think, let's just set that variable right there in the code. And let's call it deny by default. And then it's going to be true across for everything. But the reality is, every line of your specification has to account for this basic design principle. It's an emergent property of your entire specification. And you compose the different pieces of your specification to infer automatically that this global property holds. The theorems are in themselves composable. Let's think about the different ways that we can, different theorems we have for wildcard matching. A pattern always matches itself. This is one theorem. The pattern matching composes with itself in natural ways. If there are no wildcards, then pattern matching is just equality. Such theorems help us incrementally build up more complex proofs. What I haven't shared with you yet is how we implement this workflow. The snippets that I've been showing, what language is that specification written in? What are the theorems written in? How do I prove it? So let's get into some implementation details. To define the IAM specification, to write it down, we use Daphne. Daphne is an open source, verification-aware programming language. You can define the specifications, prove theorems about the specification, implement your specification, and prove that your implementation matches your specification. The advantage of using Daphne is as you type your program, the Daphne verifier constantly looks over your shoulder. It's right there, looking over your shoulder, and flags your errors. It shows you counterexamples and congratulates you when you did a good job, when your proof passes. It's like, hey, well done. And when you're done, you have a proof. The thing about Daphne is it doesn't have its own runtime. So you can't go and run your Daphne program. What Daphne does do, it provides you a bunch of compilers. So you can compile your Daphne code into C#, you can compile your Daphne code into Go, you can compile your Daphne code into Python. You see where I'm going with this. Here, we translate the Daphne implementation into an efficient Java implementation. Remember the wildcard specification? I want to give you a taste of what I mean by an efficient Java implementation. It was small, it was concise, but it did what we wanted it to do. It helped us specify it. By comparison, the Java implementation is much larger, but we can have our cake and eat it too. Because all the theorems and design principles that hold for the specification also hold for our Java implementation, even though it is optimized. That is why we can get a win-win here. Okay, we're done with the implementation phase. We are marching forward on our journey. We come to the validate phase. Spoiler alert, this is the longest part of the exercise. You take all this beautiful math, and now you got to make sure it squares up with reality. How do you do it? How do you make sure that your beautiful math lines up with reality? You use the reality to your advantage. At the scale of 1 billion calls per second, you will see every corner case at least a few million times a day. This validation that we've built is built on checking whether our formal specification matches the original engine. That's our source of truth. So we take every request, every single request, run it on the existing engine, and then run it in parallel on the new engine. This is shadow authorization. The results returned to you are on the existing engine. We also track metrics. What was allowed? What was denied? The billion-dollar question, do they always match? Are the two equivalent? Pum, pum, pum. Turns out, no. In this version that we first started checking this, we are seeing about 100 million mismatches a day. That'll sound like a big number. But just remember, 1 billion a second is a much bigger number. So let's look at what happened. Because, we are builders. We seek the truth. What did happen? Turns out the specification we wrote, we truncated the milliseconds. And there was a rationale behind it. When you create a policy and attach it, policy propagation takes some time. So it seemed like an opportunity to say, how about we make the code simpler and faster? You see an opportunity, you'd want to take it. This is where we're like, well, we see an opportunity, we want to take it. But the original implementation did not truncate the millisecond. And what we observed was that if the request came in just at the right time, not a second earlier and not a second later, the engines would generate, just for a second, a mismatch. So we updated our specification to be millisecond precise, and we fixed it and launched a new version of the engine. Okay, that got fixed. The number of mismatches went down. And then we observed another corner case in how our specification handled Unicode. We fixed that too. Now, a thing you'll notice is the number of mismatches ramp up and then level up. The reason for this, evaluation is not running on a single host. The evaluation of authorization runs on millions of hosts across several hundred services. So when we launch a new version of the engine, the services slowly pick up in their pipelines. It propagates through all the different hundreds of thousands of millions of hosts, and each of the services through their CI/CD pipelines end up picking that engine. So you can see the nature of the distributed system of widely AWS through even a thing like this here. Okay, we keep fixing the corner cases. You know, you see the months, I said the longest part, the months are chugging along. The number of mismatches keep going down until we get to 0. 0 mismatches. And we evaluate a quadrillion samples. That's even a bigger number. A quadrillion samples to say, yes, now we make this the new authorization engine. It becomes the default. Here's the fun part. When it happened, it was business as usual. Nobody noticed. It was business as usual for our customers. It was business as usual for our service teams. What we were really excited about, because now we had a whole bunch of new opportunities. I've talked about, hey, we wanted to do aggressive optimizations. So let's look at that. What does aggressive optimizations mean at this scale? Here, we are looking at a latency graph for authorization in one of our most popular services. Lower numbers represent faster authorization. For example, the line in blue is at the top is the P99.9. This represents our 0.1 slowest authorization calls in the service. So how did we do? We ended up with a 65% performance improvement. Yes, 65% faster. How did we get here? The proofs allowed us to do aggressive optimizations. Optimizations in string matching, Unicode handling, and a whole bunch of other things, which we wouldn't have been able to do without the proofs in place. And to learn more about the details of this work, there's a talk today later by scientists on this team, Sean McLaughlin and Lucas Wagner, IM401. It's the last talk of the day, but go forth and check it out. The process of defining a formal spec, proving the core theorems, generating efficient code, validating it over millions, billions, trillions, quadrillions samples, helps us prove security to access to your workloads, to your data. And it sets us up to deliver features faster and more securely. When we do things to raise the bar on security, we always ask ourselves, how do we make this available to our customers? And here I want to talk about how we've taken the knowledge of the past 15 years and the ability to prove its correctness and help you achieve the same level of provable security. We do it with Cedar, an authorization building block for your applications. You can customize access control for your principals, for your resources, for your actions. It's a reasonable question to ask. What is Cedar? It's an authorization building block for your application. Why do you need an authorization building block? Imagine you're developing a banking application, and you are the CFO, and you want to define which employees can access what company bank accounts. The way the development happens today, the authorization logic will be intermingled with the application logic, and now when the banking application has to move to a mobile version, the developer, some poor developer, will have to copy-paste all the authorization logic from the original version to the mobile version. But most likely, those two will not even be implemented in the same programming language. Most applications start with humble use cases. Say this banking application starts with a few thousand users, a few hundred resources. But as it's doing well, it's growing its business, it's expanded. Say it's a US bank, and it's expanded to Europe and Asia. Now it's serving hundreds and millions of customers with several billions of resources that it has to evaluate. It now needs an authorization system that scales. We know an authorization system that scales. We've been operating IAM at scale for past 15 years. And for the security administrators, this often is so hard. For anyone who's been in regulated industries and have to work with compliance auditors, hey, who has access to what? It involves a lot of spreadsheet tracking and reviews and checklists, but there is no auditable way. Having a centralized authorization building block can help you get to a complete view on who has access to what. Cedar provides you the ability to decouple your authorization logic from your application logic. It allows you the ability to scale, and it provides security administrators a view to comprehensively audit who has access to what. And we've leveraged our experience in IAM. I keep talking about the similarities in IAM, but we've leveraged our experience here. The Cedar language takes a security-first approach. People ask us, like, why did we build a new language? Because we wanted an authorization language that uses security-first principles. We prioritize security over expressivity. We provide you the guardrails in the language design itself. It doesn't have loops. It doesn't have recursion. The language is not Turing complete, and that is by design. We formally prove the theorems, the design principles of Cedar. And of course, we plagiarize from IAM. Deny by default, deny trumps allow. The core security design principles are the same. Now, once you have Cedar, you can use the same permission system across multiple of your applications. In the same way, the IAM is the common lingua franca for over 200 of AWS services. In your banking application, you wouldn't need to copy code over, because the policies would be represented in a separate central location. Both of those applications could use the same policies. It would work outside the box. You would get consistency. So let's look at what a Cedar policy looks like. Cedar, I claim, is easy to author, because you can specify who has access to what based on your intention. So let's look at what Cedar policies are. I'll give folks a few seconds to look at that. The first policy allows admins to schedule appointments or view client records if their client is a member of all clients. Now, you can see that this is based on the role of the principal. This is what we call role-based access control, because the role of the person determines what permissions they get. Let's look at the second policy. Allow all primary doctors to view client records and refer them to specialists. This is also a policy that grants permissions. The actions that a doctor can perform is view client record or refer a client, and the resources all clients. But there is a difference here. There is a when clause. The when clause says the doctor can only do it if they are in the primary doctor's group. This is an attribute the doctor has. So this is attribute-based access control that Cedar allows. It's a new language. It's not IAM. You may ask, why did we not just use and extend IAM? Because IAM was designed for AWS. AWS APIs, AWS resources, AWS principles. Cedar is designed for your resources, your actions, and your principles. It would have been too risky to change IAM because it would have required extensive changes to make it adapt to custom resources. Go check out cedarpolicy.com, where you can write your first Cedar policy. There's a playground, you can create it, you can run policy validation, and see how would you do your authorization in Cedar. I want to dig a little bit deeper on what are the similarities and the differences between Cedar and IAM. I want you to notice there's a lot that's same. I've talked about them. Deny by default, deny trumps allow, the PARC model, principal action resource model, order doesn't matter. But there's a lot of things that are different. IAM is for AWS. AWS enforces the policies. Cedar is for you. You enforce the policies. AWS defines principles, action, resources, conditions for IAM. You define the principles, action, resources, and conditions for Cedar. In IAM, you have different policy types. SCPs, permission boundaries, identity policies, resource policies. In Cedar, there is a single policy type. The way you teach Cedar about your nouns and verbs is through something called a schema. That's how you teach Cedar about your principles, your actions, and your resources. Here you can have an employee who's a principal. They can perform different actions, such as refer a client, schedule appointment, view client record. And the resource is a client. You can specify the relationships. What's the hierarchy between the different resources? What's the relationship between the different principles? What are their attributes? So all of these things you can state in a schema. What's the power of the schema? I want to walk through this and show you this. When you author policies, whether they're manually or programmatically, Cedar provides this thing called policy validation. It lets you check, does it have errors or does it not? You have a well-formed policy that follows the grammar of the policy. But that policy can still have typos, errors, or mismatches. Cedar is something that's called type safe. The type of every principal resource attribute is known at runtime. There is runtime checking that checks, hey, do all the arguments in a request match the expected type? When they don't match, it results in runtime errors. That's true for most systems that you'd want to run. And when these types don't match, the types in the request and types in the policy, it's a lot of effort to debug for the developer, and it degrades the end user experience of whoever using the app. Cedar provides you the ability to do policy validation statically. In the time you create or update policy, you can check for those types, that ensures these runtime errors never happen. Coming to the workflow of how we prove Cedar correct, this should look very familiar to you because we just walked through it for proving the correctness of the IAM authorization engine. We build a formal spec. That's the first step. There is a difference, though. With IAM, we had a battle-hardened, time-tested system. Here, we are developing the specification from scratch. We had to work backwards from your use cases to figure out what is the specification. We met with you and a bunch of other customers who wanted an authorization building block. We considered a lot of different use cases. We considered workforce application use cases based where permissions needed to be defined based on the roles of a person in an organization. Managers wanted to be able to restrict access based on the day of the week. Use cases for zero trust needed to secure access based on the identity of the person, based on the device posture. You can see how this can help in zero trust. User-facing applications such as documents sharing, photo sharing, are more role and relationship-based. Here, the use cases were, hey, can I organize my resources into hierarchies, photos into albums, groups, and teams? You can learn more about the design of Cedar from this reInvent talk by Amina Torlak, a senior principal applied scientist leading the development on Cedar, from a reInvent 2022 talk. OK, we move to proving the properties of Cedar. Again, deny trumps allow, deny by default. We bake in the security learnings on day one. We prove other properties as well. Order doesn't matter. And all the policies that are validated do not have any runtime errors. OK, chugging along, implementation details. Cedar is open source. It's available. You can go check it out. We implement the proofs in a language called Lean. We have a specification and an implementation in Lean. We also have an efficient implementation in Rust. The Lean proofs are open source. The Rust implementation is open source. The policy validation is open source. We've built this authorization building block for you. Go check it out. We automatically generate tests to show that the implementation in Lean and the implementation in Rust behave the same. A partner, StrongDM, added a Go implementation for Cedar, and they use the same verification guided development process that we have for the Lean and Rust process. Finally, coming to validation. We don't have a system that runs 1 billion times a second to validate that things exist. This is different from IAM. So rather than compare it to an existing engine, Cedar has an RFC process to get feature requests from you. Based on the feedback, we added a new operator, the is operator, to Cedar. Similarly, there's other examples of features. You can go through, check it out. Once you start playing with Cedar, once you start using Cedar, you can use the RFC process to add more feature requests to it. Great. Are we there? Are we done? Not quite. The IAM service is a lot more than the evaluation engine. In this reInvent talk, Becky Weiss, a distinguished engineer in AWS, talks about the architecture of IAM. When you create a policy, how it's created, how it's stored, how it's propagated. There's a lot behind it. And to do all of that, you need a control plane. You need a data plane. You need propagation, a lot of it. So it's not just a building block. It's an entire ecosystem around it. Similarly, for Cedar, we have Amazon verified permissions. It's a managed service to create Cedar policies, to manage them, to evaluate them. It's the entire service. You don't have to do logging. You don't have to do your own management. You don't have to do your own scaling, your own control plane, your data plane, how many hosts you want to run Cedar on. Verified permissions does that for you. There's several applications verified permissions can support. It can do applications such as serverless and container workloads, databases. All of these you can use for authorization. Likewise, if you're a developer, you'd want to use policies as code. You'd want to use it for different IDPs. You'd use it for logging. Think about it. There's so much to it in your authorization. To wrap up, in the world of mathematical logic, we've come a long way from Euclid. Euclid's reasoning of the Pythagorean theorem to proving security of your guardrails in the cloud. The fundamentals are the same. With one click, you can get S3 block public access or IAM access analyzer. You've taken Euclid and turned them into one click. The automated reasoning engines reason about infinite requests, infinite policy requests, infinite network configuration, infinite code paths. And the power is we do this all on your behalf. That's the power of the click. You don't have to think about, how do I represent my bucket policy in math? How do I represent my specification in math? What is the definition of public? You don't have to think about any of those things. We call this provable security, and we prove properties of your networks, of your reachability analyzer, network access analyzer. We deployed a provably correct version of authorization, and you had to change nothing in what you do, and you get the benefits of it. That is how we keep raising the bar on security. Over the past several years, you asked us to provide a building block like IAM. And we built the Cedar policy language for your applications. In the way IAM is for AWS, Cedar is for you. We believe authorization is going to be a key security pillar moving forward to achieve your security goals. The ability to implement zero trust architectures based on least privilege, the ability to specify access based on device posture, identity, and context information, such that is this employee on call? I want you to think about how you're doing authorization within your applications, both for brownfield and greenfield application. Separate your authorization from your application. Get the level of assurance and correctness in the authorization of your code when you use Cedar. Audit the permissions using verified permissions. Do it all. As you leave this Reinforce, look at how provable security with Cedar and verified permissions can help you with your security. Thank you for coming to Reinforce and these sessions. There's a couple more sessions on provable security and automated reasoning if you want to go check it out. And please take the time to fill the survey. We use the feedback to bring the content you are most looking forward to. Thank you again.